we're happy to continue with the talk of Arnaud Maret, who will tell us about complex projective spaces via surface group representations.
Yeah, thank you very much. Thanks for the opportunity to talk here. And yes, so today I want to explain some correspondence between the complex projective space and character variety of surface group representations, which was the topic of my PhD thesis, actually. So let me start with saying a few words about surface group representation, because I don't assume everyone is very familiar with this kind of spaces. So what do we want to look at? We want to pick a surface. So you pick your favorite surface S and put some orientation on it, and you pick a Lie group G. And the space you want to consider is the space of group homomorphism from the fundamental group of the surface S into G. And actually, you don't want to look only at homomorphism, but only at conjugacy classes. So this quotient that we take here is the quotient by the conjugation action of G on that space. So given a homomorphism on an element of G, you can conjugate it to produce a new homomorphism. And that's the quotient we want to take. And the resulting space is what we call character variety of the pair S and G. So this is, you can put a topology. The topology is essentially coming from G when you think of pi1s as being so a finitely generated group. So you can put the discrete topology. The quotient might make things a little bit complicated because its action is not so nice, but we don't really care about the singularities. And we'll just assume that the character variety is smooth. So the question is, why should we care, right? Like, this is a symplectic seminar, so why should we care about character varieties? Well, because they are very symplectic in nature. So the main result here goes back to Goldman in 1984. If the surface S is closed, then these character varieties have a natural symplectic structure. Which we refer to as the Goldman symplectic structure. So the work of Goldman was partially inspired by the work of Attia Bott in their paper on the Young-Mills equation. And in the more general case where S has boundary components, then the structure you put on the character variety is the Poisson structure. And once you fix some, once you constrain the behavior on the punctures, or let's say around the boundary of the surface, then this corresponds to looking at the symplectic leaves of this Poisson structure. And another thing you might be interested in is that not only this is somehow a recipe to build a symplectic space from a surface and a Lie group, but it comes with a natural action of a group that's interesting on its own, namely the mapping class group of the surface. So the mapping class group of the surface is the group of let's say, orientation preserving homeomorphism up to isotopy. And this acts on the character variety. How? Well, given a diffeotopy on S, you get, it induces an automorphism of the fundamental group of S, well, the conjugacy class of automorphism. So given a representation, you can precompose it by this automorphism of the fundamental group, and this defines for you the action on the character variety. And the good thing is that this action preserves the symplectic structure. So a character variety is in a few words, it's a symplectic space, or let's say Poisson, that comes with an action of a well-studied group, like mapping class group, which preserves all this structure. Okay, so that's the general theory about surface group representation. Now for this talk, because I said complex projective space, so we need some compactness. So we're going to look for compact examples. So how to get a compact example? Well, the first method, which is probably the easiest one, is just to take G to be compact. If your Lie group is compact, then the character variety is compact. Well, for today, we'll consider this cheating, and we'll look at another kind of example, but which is not obvious a priori, how to get a compact character variety, or let's say a compact component in some character variety when G is not compact. And that's somehow like the kind of representation I'm trying to sell to you today, which are these so-called totally elliptic representations. So what is a totally elliptic representation? So again, we are looking at representation from fundamental group of surfaces into Lie group G. We're going to say that the representation is totally elliptic if it maps all the simple closed curves on the surface. So simple mean no self-intersection. So you take like connected one-dimensional submanifold of the surface, if you prefer. You want to send all the simple closed curves to an elliptic element in your Lie group G. So in general, we'll say that an elliptic element is, well, an element of a maximal compact, let's say, in G. But we'll be primarily interested in the case where G is PSL2R, so the isometries of the hyperbolic plane, in which case, well, elliptic means probably the notion you're familiar with. This means that when you act by isometry on the hyperbolic space, you have a unique fixed point in the interior. So you act somehow by rotation around this point, or you can say trace smaller than 2 if you want. So that's what totally elliptic means, totally elliptic representation. And why do we care about totally elliptic representation? Because they're closely connected to compactness property. For instance, if again, if G is PSL2R, then this is actually a theorem. You can prove that any component of totally elliptic representation in PSL2R will be automatically compact. And if now G is a bigger group, let's say a bigger dimension or bigger rank, then all the examples we know of components of totally elliptic representation are compact, and surely there's a way to get a direct implication here. Okay, so
could you please remind? So what is
yes.
what is exactly S? Is it a surface, just a surface, or
S is just an oriented surface?
So when S is a two-dimensional torus, can you just illustrate, because then we more or less understand?
Yes, right. So,
okay.
Sorry, but you want me to illustrate?
Yes. So illustrate the notions which you introduced in the example when S is torus. So then you have Z2, right?
Right. Then the fundamental group is Z2. Yes. So one way to, well, okay. So maybe one way to think about it is that once we are given such a representation of a surface group into G, somehow, if G is PSL2R, you want to think about hyperbolic structure you put on the surface, and your representation as being the holonomy of this hyperbolic structure that's like connected to this notion of Teichmüller space. But here, in the case of the hyperbolic structure, then you will map all the element to hyperbolic element. So here we really want to go away from this smooth, nice hyperbolic structure in a world of representation where we map this simple closed curve to elliptic elements. So we are going to parameterize a singular hyperbolic structure, again, in the case where G is PSL2R. And maybe an easy example of a character variety, think of, you know, like if you take a surface whose fundamental group is maybe, you know, let's say a free group on one generator, then an example of the character variety is then just the space of conjugacy classes in G. That's an example. So I'm not saying a lot of things about the genus 1 torus, but I'm trying to you know, motivate surface group representation from a different perspective.
Please. Excuse me, please. And do you have any examples where your image is not just a maximally compact subgroup?
Yes. Yeah, of course. So that's the whole point. Like, so the examples I wanted to cite now, all the examples we know, like all the, let's say, non-trivial examples we know of totally elliptic representations exist for punctured spheres. So the main source of examples comes from this paper of Bertrand Deroy and Nicolas Toilozan in 2020, where you build actually components of Zariski dense totally elliptic representation. So in particular, the image is not contained in a maximal compact. It's really Zariski dense in the group PSL2R. So yes, and the whole component consists of only Zariski dense representations. So that's the whole point. That's what is somehow mysterious about these things, because at first maybe you would assume that it's not possible to build such examples, but we have them. And the way they're constructed is they come from reflections through sides of non-convex polygons in the hyperbolic plane. That's how you build them. But the bottom line is that it's always a representation of a punctured sphere. Like in PSL2R, you can prove that you cannot have genus because the commutator of 2 elliptic is always a hyperbolic element in PSL2R. And this was generalized later on in 2021 by Tolosa and Toulis, who were able to build similar components, but where you can replace PSL2R by any Hermitian Lie. So for instance, PU21, the isometries of the complex hyperbolic space, or all the PU-PQ, also higher rank, and always components for punctured spheres. So we do.
But it means that
yes.
It means you consider just you demand only that the simple curves correspond to elliptic elements, but non-simple.
Non-simple can do whatever. I'm restricting.
Okay.
Maybe since you asked the question, I mean, the motivation behind this comes from conjecture. Like maybe you're familiar with this, like the Bowditch conjecture for representation into PSL2R. So if you have a representation of a closed surface group in PSL2R that maps all non-trivial elements to hyperbolic elements, then it's the holonomy of a hyperbolic structure. So then Bowditch asked, what if I only map simple closed curve to hyperbolic element? Is that enough to guarantee that I'm the holonomy of a hyperbolic structure? And that's still an open question. So somehow we take the counterpart and say, okay, let's look at components where we map all the simple closed curve to elliptic elements. Right. So now what I want to do, I want to insist a little bit on these examples coming from Deroy and Tolosa in 2020. So here, sigma n is a sphere with n punctures. And so what is exactly the space we are looking at? So first of all, because we are mapping every simple closed curve to elliptic elements, we also have to map the boundary curves, so the curves around the punctures to elliptic elements. And in order to get a nice moduli space of representation, because here we have a non-closed surface, what we do is we prescribe the boundary behavior around the punctures. So we are actually going to fix the conjugacy classes for the image of the loops around the punctures. And since we are in PSL2R, we are fixing an angle between 0 and 2 pi. And in that space chi alpha, I'm only looking at representation that maps the boundary curve around the i's puncture to an elliptic element with angle of rotation alpha I. So this is what people call a relative character variety, so relative to alpha. And in that space, so this space is not compact, but the point is it has a compact component. And this compact component is what I denote by chi dt alpha. And this was the compact component discovered by Deroy and Tolosa, as I said, in 2020. And I'm not exactly going to explain to you how this representation are constructed, but I'm going to tell you how we can identify this component with a complex projective space. So here we go. The idea is that we're going to use this property that the representation are totally elliptic to build a torus action on our component. So how does this work? So on the left here, on the right, you have a picture of the punctured sphere. And in green, you have a collection of simple curves, non-intersecting simple curves. So if I pick one of them, like the curve A on the left, I can define the following function on the character variety. To a conjugacy class of representation rho, I associate the angle of rotation of the element rho of A. So remember that rho is totally elliptic, so it will map A to an elliptic element, which I can measure the angle. And this angle is an invariant by conjugation, so this function is really defined at the level of the character variety, so on the quotient. So it's a function with value between 0 and 2 pi, which I think about now as a Hamiltonian function on my compact symplectic space. And I'm going to look at its Hamiltonian flow. And the first thing we can compute is that all these flows, so no matter which curve each curve A you pick, there will always be pi periodic. So they all have the same period. And another observation you can make, which is not too hard, is that if you look at the flow coming to two disjoint curves, so here A and B are disjoint, then their flow will commute. Right. So what do we do now? Let's try to take the maximal number of such flow we can take. which is, well, it's simply the maximum number of a non-intersecting simple closed curve on this punctured sphere sigma n, which turns out to be n minus 3. And now that's where the little magic happens here, because n minus 3 is also half the dimension of the character variety. This is another thing you can compute. So what does it mean? It means that these Hamiltonian flows that are periodic and commute that I introduced here will give you an action of an n minus 3 dimensional torus on your character variety, a Hamiltonian action. And because n minus 3 is half the dimension of the character variety, this is a maximal torus action. And this actually turns your character variety into a symplectic toric manifold. So this was mentioned in the previous talk. What do we do with symplectic toric manifold? We can associate to them their moment polytope. And that's what we do. We compute the moment polytope of this action. And then we use this classification of symplectic toric manifold. We open our big list of moment polytope. And we observe that the moment polytope associated to that compact component, that compact character variety, turns out to be the same as the moment polytope for the standard torus action on the complex projective space, which by Delzon's classification implies that the two spaces are actually symplectomorphic in an equivariant way. And the right dimension of the complex projective space is obviously n minus 3. Okay, so now we have this identification. What do we do with this identification? Well, I told you at the beginning, there is this interesting action on the character variety, which is the action of the mapping class group. So in this case, the mapping class group of the punctured sphere. And the mapping class group has a nice family of elements, which are also generators, which are called dent-twists. So here's a picture of what a dent-twist is. So given a simple closed curve, so in green, A here on the surface, what a dent-twist does, so it's an isotopic class of homeomorphism, which are supported in small neighborhood of the curve A, and you basically do a full twist of this neighborhood and glue it back in the surface. And that's a twist, that's a dent twist. As I said, dent twists generate the mapping class group, so they are pretty interesting elements. And there's another somehow magic formula here, which is the following. The dent twist as a symplectomorphism of the character variety actually can be computed from the Hamiltonian flow of the corresponding angle function. So A is a simple closed curve. I have this angle function that I defined before, theta A, and I can look at its Hamiltonian flow. And if I take the flow at the time, well, depending on the function, theta A over 2, then this Hamiltonian diffeomorphism turns out to be the same as the dent twist acting on the character variety. So the conclusion is that not only the action of the mapping class group is symplectic, but it acts by Hamiltonian diffeomorphism. And another thing you can check is that the mapping class group acts faithfully, so a non-trivial element acts in a non-trivial way. And the bottom line is that now we can think of the mapping class group of the punctured sphere as a subgroup of the group of Hamiltonian diffeomorphism of this compact character variety, which I explained before can be identified with the complex projective space, right? So what do we do from here, right? We have this group of Hamiltonian diffeomorphism, which people like to study. And if we think of the complex projective space as being this character variety, then the good thing about in this interpretation is that it gives us this interesting subgroup of the group of Hamiltonian diffeomorphism of CPn-3, namely, again, the mapping class group of the sphere with n puncture. So here's something I've just started to study with Vincent Humilier here in Paris. On this group of Hamiltonian diffeomorphism of the complex projective space, you have this so-called Entov-Polterovich quasimorphism. And so you can take this quasimorphism and you can restrict it to this subgroup, the mapping class group of the sphere with n puncture. And what you get is a quasimorphism of the mapping class group of the sphere with n punctures. So it's a very fresh project. But what we've been able to do so far is we've been able to compute the value on dent twist. So I explained to you before that dent twist can be seen as somehow the flow of the angle function. And what our computation shows, so I spare you all the integrals here, is that the value of the quasimorphism on den twist is some constant that depends on the angle alpha that I have fixed and n the number of punctures times this quantity, which is k minus 1 times n minus k minus 1, where k is the number of punctures on one side of the curve A. So remember, A is a simple closed curve on the punctured sphere. So it cuts the sphere into two parts. And on one side, you have k puncture. On the other side, you have n minus k puncture. So you see that this expression is symmetric. And somehow the value of the quasimorphism on the den twist only depends on this number of puncture on each side of the curve A in this fashion. So the first question we ask ourselves is, well, is this quasimorphism of the mapping class group already known quasimorphism of the mapping class group? So it's interesting to see that here the value on den twist is in particular non-zero because we have this expression. And for instance, if one way people have built a quasimorphism for mapping class group, following the work of Betsvina and Fujiwara, is by looking at the action of the mapping class group on some delta hyperbolic space. So for instance, the space of curves, the curve graph of the surface. But if you do such a construction and you homogenize the quasimorphism that you get at the end, what you'll see is that it's going to vanish on the stabilizers of points. A point in the curve graph is a simple closed curve. An element of the stabilizer is a den twist. And so you'll see that you actually vanish on den twist in this construction, and here in our construction we don't vanish on den twist. So that's an interesting observation. And maybe the last remark I want to say. So I don't have much more to say about this because again it's fresh work. There might be some connection because the mapping class group of the punctured sphere is more or less a braid group, and there are other examples known of quasimorphism for braid groups, which, according to some preliminary computation we've made, might give you a similar formula for the value on den twist. So we are kind of exploring how close is this connection between like the restriction of the Entov-Polterovich quasimorphism on the mapping class group and these quasimorphisms on braid groups defined using invariant of nodes, like signature of nodes and so on. All right, that's everything I wanted to say. Thank you.
Thank you very much. Are there any questions from the audience?
I guess an easy one. If you consider the case k equals 1 in your theorem, you just get 0. Is it just because you fixed the angle alpha to start with?
Yes. So okay. So we don't twist around the punctures, like, because I mean these are part of the details I didn't say, but twist around the puncture is trivial essentially. That's like
okay, that's clear. Okay.
So we have at least 2 punctures on each side of the simple closed curves.
Yeah, thanks.
Which kind of techniques are you using to prove this theorem, to calculate this quasimorphism?
Actually, we're just using the fact that there's a Hamiltonian function that generates like the den twist as a Hamiltonian diffeomorphism that's constant on the Clifford torus in the variety, and then the value is basically given by this constant.
I see, thank you.
So it's just have to compute some integral.
Are there further questions? So if there are no further questions, let's thank Arnaud again. Thank you, Arnaud.